Good morning, ladies and gentlemen. Welcome to Physics 20, Work, Energy, Power, Lesson 5, the Work Energy Theorem. Now, as a warm-up and a review, what's the spring constant K of a rubber band that needs 11 joules of energy to stretch the rubber band 34 centimeters? Well, first thing you do is draw a picture. Here's the rubber band. Here's the rubber band being stretched. X distance, which is 34 centimeters, 0.34 of a meter. Now, we talked about energy of a rubber band, 1/2 kx squared. So 11 joules is 1/2 times k times 0.34 meters squared. Now, I prefer to leave it, since we're doing SI units, so everything should be meters and kilograms and all that stuff. Anyway, so 11 joules is 1/2 k times 0.1156, 11 joules equals k times 0.0578 meters squared, so divide both sides by 0.0578, and k equals 190.3, I'm going to call it 190 newtons per meter. Okay, that works for me. Now moving on to today's lesson, Work Energy Power Lesson 5, the Work Energy Theorem. Here I want to stress that the work done is equal to energy transferred. So work is force times distance, energy 1/2 mv squared. So work is energy and energy is work. All right, so that's the big thing here. If you've got that, you've got this lesson. Now, let's do a couple of examples. You're driving your 1,200 kilogram truck at 50 kilometers an hour when a child runs in front of you. You slam on the brakes and stop in 18 meters and miss the kid. Good. What's your braking force? Well, as we just said, work done is change in energy, or force times distance is 1/2 mv squared. Now, what's your braking force? We want the force, so let's go 1/2 mv squared divided by d will be our force. Now I feel like rearranging the equation right now, whatever. So it's 1/2, the mass is 1,200 kilograms. Oh, so here, orange is the back color, sorry. My apologies, talking to myself. Divide by 3.6, because it must be in meters per second. We get 13.77, which is 13.8 meters a second. All that divided by the distance, 18 meters. So force, grab your calculator. That's 114,264 joules by 18 meters. So the force is 6,318 newtons. Sorry, 48 newtons, my apologies. 6.3 times 10 to the 3 newtons. Now notice that's a lot easier than V initial, V final, acceleration, displacement, time. And honestly, you do a few of these, you can cut out some of these steps. You guys are showing me you're sharp. But let's practice this a little bit more. So, you're driving your 1,200 kilogram truck by the mall when you slow down from 100 kilometers an hour to 80 kilometers an hour in 120 meters. What's your braking force? Well, once again, work done is change in energy. Now, notice I said change in energy. I should be changing change in work, because that's energy final minus energy initial. Okay, so force times distance is energy final minus energy initial, or 1/2 mv final squared minus 1/2 mv initial squared. Okay, now what were your initial and final speeds? Well, 100 kilometers an hour is 27.7 meters a second. 80 kilometers an hour is 22.2 meters a second. So don't do the rounding up, use these rounding off numbers. Use the correct numbers when you do the calculation. Anyway, so force times 120 meters, 1/2, 1,200 kilograms, times 22.2, meters per second squared, minus, and I need a little more space. There we go. 1/2, 1,200 kilograms, times the original speed was 27.7. So, plug in the numbers in. Force times 120 meters. Notice this time I didn't divide by d first. I don't know why. 295,704 joules. The joule, not a 5 at the end, my bad. Minus 460,374. And your numbers might be slightly different depending on whether or not you use the round off numbers. Don't. Anyway, so force times 120 meters is minus 164,670 joules. 120 meters. It's a joule, not a 5, dear. So force is minus 1372 newtons. Minus 1.4 times 10 to the 3 newtons. And notice how much easier that is instead of V initial, V final. All right? Now, a few more questions and I'll leave you alone. You throw a 0.5 kilogram basketball straight up. If the speed of the ball is 3.9 meters a second after you accelerate to a distance of 0.78 meters, what's the force you apply on the ball? Okay. Well, here, draw a picture. Here's the basketball. Here's the basketball going straight up. So you have force applied. Now, what's wrong with this picture? What have I forgotten? Yes, force of gravity. We always have gravity. Oh dear. So now this is a force net question, which is force applied plus force of gravity. And what else do we know about net force? Yes, net force equals mass times acceleration. So we need to figure out the force applied. We know force of gravity is mg. 0.5 kilograms times 9.81 meters per second squared. That works out to be minus 4.9 newtons. All right, now, here we have acceleration we have to calculate. Crap. I mean poopy. Kinematics again, like we haven't done this before. Well, V initial is 0. V final is 3.9 meters a second. Acceleration distance, 0.78 meters. So we need to, excuse me, figure out acceleration. We don't have time. Let's see, final squared equals velocity initial. Kazad. And I meant that. So V final 3.9 squared equals 0 squared plus 2 times a times 0.78 meters. 3.9 squared is 15.21 meters squared per second squared equals 2 times 0.78 is 1.56 meters times a. So we divide both sides by 1.56 meters. A is 9.75 meters per second squared. So net force, force applied plus force of gravity. So mass times acceleration, 0.5 kilograms times 9.75 meters per second squared equals force applied minus force of gravity, 4.905 newtons, Let me see. This 4.875 newtons equals force applied minus 4.905 newtons. No, I don't like that color. I add 4.905 newtons to both sides. Force applied is 9.78. Okay, see how that goes? All right, so sometimes we still have to do the V initial, V final acceleration displacement time questions just to screw with you. I don't like that question. Let's do pink. All right, you're firing a 250-gram rocket. If the motor generates 30 newtons of force for 15 meters, what's the final velocity of the rocket? Well, work done. Oh, come on. Don't be like that. Changing work is changing energy. Force times distance is 1/2 mv squared. That's not a very nice m. So we're solving for velocity. So velocity squared equals force times distance divided by 1/2 the mass. Actually, I should show you that. I just shouldn't write that out. That's a little bit rude of me. Divide by both sides by 1/2 mass. There we go. Now, that's 30 newtons of force times a distance of 15 meters divided by 1/2 the mass, 0.250 kilograms. Grab Mr. Calculator, plug that in. That's 3,600 meters squared per second squared. Square root that. Velocity is 60 meters a second. All right. This is what I need you to be able to do. Now, last question, just to confuse you. The rocket from the last question slams into a concrete wall, compressing the nose cone 4.5 centimeters. What's the spring constant K of the nose cone? Well, here, you have to go, what the heck, springs? Yes, we talked about it earlier. I expect you remember it. Plus, have you ever fired those model rockets in a basement? My brother made a bazooka out of those. And anyway, we'll talk about that later. So, work done is change in energy. So force times distance is the energy. Now here, what energy are we talking about? Not kinetic, elastic. So we have the force. Do we have the force? We have the distance. We have x squared. We have the distance. Let me think. Yep. We have d, which is x. We're looking for k. We know. Force. Sorry. Force, MAD. Mass times acceleration. So we know the mass of the rocket. We have to figure out the acceleration. Another one of those questions. So the initial is 60 meters a second. Final 0, acceleration distance 0.045 of a meter. We don't know time. So I go V final squared, V initial squared plus 2AD. Zero equals 3,600 meters squared per second squared plus A times 0.09 meters. Subtract 3,600 from both sides. Minus 3,600 meters squared per second squared equals 0.09 meters times A. Divide both sides by 0.09. Acceleration is minus 40,000. And that does seem like a lot, but no, it's not actually. Well, it is a lot, but when you're playing with rockets, yeah, it's a lot. So let me see now. I know mass, I know acceleration, I know distance. Yeah, oh, say solving for k. So here I divide both sides by 1/2 x squared. 1/2 x squared. So k is MAD over 1/2 x squared. Plugging the numbers in. So I need to move down a little bit. Acceleration was minus 40,000 meters per second squared. That's times. And the distance 0.045 meters. 1/2 is 0.045 meters. We're squaring that. And yes, you can cancel that out if you want. That becomes 444,444 newtons per meter. 4.4 times 10 to the 5 newtons per meter is the spring constant for that nose cone of the rocket, which suggests it wasn't foam or something soft. A little bit hard. A little bit of an owie if you stop it with your face. Not of an owie, actually. And if you remind me in class, I'll tell you that story. Anyway, any questions about this?